Okay, so welcome back to case 2. Right, so what we have is two cuts. C is a separating cut that is not tight. We want to prove that B of G is strictly less than B of G1 plus B of G2, where G1 and G2 are the C contractions. Right, what we do have is a tight cut as well, and the two cuts are crossing. And the two contractions for D, we are calling them H1 and H2. But because this is a tight cut, we have this B of G is equal to B of H1 plus B of H2. Yeah? And from here, we need to somehow get here. Okay? Good. So, let's see what we can do. We have these two graphs, H1 and H2, and we want to somehow rotate and get here. Right? So, we will do exactly that. We will somehow rotate things and get there. So, to rotate we need some space, so there is some space here, here, here and here. So, we'll look at the two eye contractions of H1. Yeah, let's look at the two eye contractions of H1. Let's just draw them first and then we'll think about them. Or maybe I should use my convention, yellow arrows. Okay. I'm going to draw the two eye contractions. This is an odd set, so good. At least the graph will have even number of vertices. That is good news. I'll keep this as it is, and I will shrink everything else into a single vertex. So this is my set X intersection Y. And everything else, this vertex along with this set, will become a single vertex. I will not even label vertices anymore, right? So this is one eye contraction of this graph H1. Let's draw the other eye contraction. So now I will keep this and this as it is. So this becomes a bit messy, but anyways, I won't even bother. I'll keep this little y bar. This is X bar intersection Y. Just to remind you, this is an even number of vertices. And this fellow will become a single vertex. Let me just throw some edges. Okay, fine, good enough. Yeah, let's call these graphs H11 and H12. Yeah, fine. Yeah, and we'll do similar thing here. Let's just finish the drawing so that I can free up my physical work and focus on the mental. So I will draw the two U contractions. So now what do? I keep this set as it is. This is X intersection Y bar. This is an even number of vertices. This vertex is little y. And this whole thing becomes a single vertex. And I will call this H21. Yeah? And now let's draw this fellow. I will keep this as it is. This is X bar intersection Y bar. This is odd. And all of this will become a single vertex. Okay, so let me put it like this. Let me call this H22. Yeah? Everybody's happy with these drawings? Okay? Reasonable? Okay. Of course, why can we do this and what can we do with this? Let's try to figure out. It would be nice if these are matching chord graphs. So we should at least try to convince ourselves first that this is a separating cut here. Can we say that I is a separating cut in H1? Can we say that I is we know that I is a separating cut in the original graph G. That we have already concluded. I and U are both separating cuts in G. So using the usual arguments, right? Take any edge here. That edge exists here. Take a perfect matching that contains that edge and meets the cut I in exactly one edge. And observe that, let's just make sure, the cut D is a tight cut. Cut D is tight. Its restriction here will be a perfect matching of this graph with the desired properties. We are using crucially the fact that D is tight. Yeah?
I was just saying, like, we just did this in case 1.
We did this, right?
Like,
yeah.
This is a tight cut,
this
is a separating cut, that's laminar.
Right, then it works, yeah. So in fact, this is not a very optimized presentation. But yes, so in fact, that is one of the DIYs. Optimize to the extent you can, which is what Lucchesi Murthy do actually. I am presenting a less optimized version deliberately. Yeah. So there is some repetition and it is partly deliberate so that you can find the common patterns. But yeah, thanks. That's a good point. So it's exactly the same argument and therefore there is a lemma here which can be extracted and you don't need to repeat all of this. Right? So it is indeed a separating cut in this graph. Yeah. And we get the 2C contractions, they are matching covered. Right? Now the same argument goes through here. Exactly the same thing. U is a separating cut in H2. Therefore, what I have drawn are 2 matching covered graphs. All good? Yeah. So let's write down. So therefore, by the induction hypothesis, B of H1 is less than equal to B of H11 plus B of H12. B of H2 is less than equal to B of H21 plus B of H22. Yeah? Remember, we are trying to prove a strict inequality. Somewhere we should get a strict inequality, otherwise it won't work out. Right? So, can any of these be made stricter? Can we make any of these stricter? We observed earlier that I, at least one of I and U, without loss of generality I, is not tight in G. I is not tight in G. Therefore, I is not tight in H1. Take a perfect matching in G that meets the cut I in 3 or more edges. Observe that its restriction is a perfect matching in H1 that meets the cut I again in 3 or more edges. So therefore, because of this, we know that I is not tight in H1. So by the induction hypothesis, we can make this a strict inequality. Yeah, all good so far? Yeah. Yeah. Okay, so now let's put all of this together and see what we need to do in order to reach here. Yeah. So B of G is equal to B of H1 plus B of H2. Because of this strict inequality, now I get a strict inequality here. I will replace them by these terms. H11 plus H12 plus H21 plus H22. Yeah? Everybody agrees? So far so good? Right? But we want to get to G1 and G2 somehow. Well, the way things are written, right, it's not very nice. To get to G1, we should somehow take these two together. And to get to G2, we should somehow group these two together. Right, so we just need to change the grouping. Let's change the grouping. I want to put 1, 1 and 2, 1 together. B of H11 B of H 2, 1. These two seem to be related to this fellow. And now let's take the other two, 1, 2 and 2, 2. They seem to be related to this fellow. Not done anything. Very innocent rearrangement. Yeah? Everybody's with me so far? Any questions, concerns? All good? Now let's see if there is actually a relation. What's going on here? Is there a way, remember we want to get to G1 and G2. Is there a way to get to H11 and H21 from G1? That is right. Right? These two are nothing but the I contractions of this graph. And these two are nothing but the U contractions of this graph. Let's see. Let's just here, if I want to take the I contractions, what would I do? I would shrink all of this into a single vertex. You'll get exactly this graph. Is that correct? No?
It does not seem like it. The set of edges seems like different.
Is it? So which one are you concerned about? Are you concerned about this fellow or this fellow?
Maybe let's talk about that.
Yeah? Okay. So I claim that this graph, the way we got it, we can simply get it through this way. Right? Let's see what we are doing. We are basically shrinking. How is this obtained? This is obtained by shrinking the complement of x intersection y. So I have x intersection y, I want to shrink the complement. Shrinking the complement is as good as shrinking any subset of the complement and then shrinking the rest. So this is clear, right? Whether I first shrink the right hand side and then I shrink everything else, or whether I first shrink the bottom part and then I shrink everything else, I will get the same graph. That part is okay. Yeah? This is fine. Let's think about this now. What about this? Here we are shrinking. Here we are using something. This is fine and this is also fine by symmetry. Let me actually put orange arrows here. This is fine and this is fine. What about the other two? Are the other two arrows, is this one valid? Is this one valid? Have we done something similar before? Have we done something similar before? We are using some fact. So what you could do is you could define two graphs here. You can call this G11. Observe that G11 is equal to H11, and then you can define, so this is one way to do it. You can define G11 and observe that these two are equal, and you can define G12 and observe that these two are the same. I'm not drawing G11 and G12 because they are the same as these two. But to claim that these two are the same, G12 and H21, we are using some fact over there that we have used before when we proved Lobach's tight cut decomposition theorem about bonds. There was this exercise I gave which was about bonds, two crossing bonds, and you have no edges between the two even quadrants. That there are no edges between this and this. That actually tells you that these two graphs will be the same. Do I need to say up to multiple edges? Let me see. Yeah, please check. I think these two are not actually isomorphic. They are the same up to multiple edges. Similar to what happened in Lobach's proof. So what we are doing in Lobach's proof, if you recall, there was a point where we were keeping the even quadrant as it is. Then in one case we were shrinking this first, and then we were shrinking this part. In the other case we were shrinking this part first, and then we were shrinking this part. That's exactly what is happening here. What is this graph? We are keeping this quadrant. We have shrunken first. How did we get to this graph? We first shrunk this into a single vertex, and then we shrunk this into a single vertex. Right? We first shrunk the left part and then the bottom right quadrant. Now what we are doing here is we are first shrinking the bottom part and then we are shrinking the top left quadrant. That will be the graph G12. These two graphs need not actually be the same, but they are going to be the same up to multiplicities of edges. And the reason for this is that there are no edges between the two even quadrants. That is a lemma we used in the proof of Lobach's theorem. So that we are using here. So this is the more tricky part. They are not actually the same up to multiple edges. G12 and H21. I have not drawn G12, you get the point. Right? You shrink this into a single vertex, that will give you G12. And similar thing happens here. You get a graph. This is going to be my G22, that is the same as H22, but G21 is not the same as H12. They will be the same up to multiplicities. So therefore, this quantity can therefore hopefully be related to H11, H21, related to G1. We want to relate this to be of G1, and we want to relate this to be of G2. Yeah? Make sense? So can we relate this to be of G1 and can we relate this to be of G2? So what can we say about I in G1? Huh? Not tight? Supposing I is not tight in G1. Supposing I is not tight in G1. Then there is a perfect matching that meets the cut I in 3 or more edges. Only one of those edges can go to this vertex. The remaining 2 edges go to the other quadrant. Now I can extend it to a perfect matching in the original graph that will meet the cut D in more than one edge. Contradiction, D is a tight cut. If there is a perfect matching that meets this cut in G1 in 3 or more edges, one of those edges can go to X bar because it is a single vertex. The other 2 edges or more will have to go like this, from this quadrant to this quadrant. Now map it back here. Now the same perfect matching, you can extend it to a perfect matching in the original graph. That will again meet the cut D now in 2 or more edges. So we actually proved that I is tight in G1. I was not tight in G, but in G1 it has actually become tight. And by the same argument, U is tight in G2. If not, then you have a perfect matching that meets the cut in 3 or more edges. One can go here. The remaining 2 will go like this. They will look like this here. They will meet the cut D in more than 2 edges. That perfect matching. So in fact, I and U are tight in G1 and G2 respectively. So what we have here is an equation. This is equal to B of G2, B of G1, and this is equal to B of G2. And here we are using the fact that I is tight in G1 and U is tight in G2. And if you believe that, then what we have is B of G1 plus B of G2. B of G is less than B of G1 plus B of G2. Proved. But there are a lot of subtle points. Let's go through it carefully. Let's make sure that the drawings are not fooling us. Right? So let's just see what we did. We took our cut C, separating but not tight. We want to prove that B of G is strictly less than B of G1 plus B of G2. So G1, G2 are the C contractions. And we are in the case where we have a non-trivial tight cut that is crossing this cut. So that is the cut D. And because it is a crossing cut, because it is a tight cut, we can directly say that B of G is equal to B of H1 plus B of H2, where H1 and H2 are the D contractions. This is fine. All of this is just the same thing we did in case 1, nothing different. The difference is they are not laminar. So we can't do exactly the same thing. Right? So we go to this more complicated drawing and we want to get from H1 and H2 to G1 and G2. One way to do that is to somehow rotate things around. Right? So take the 2 I contractions of this graph, take the 2 U contractions of this graph, and observe that I and U are indeed separating cuts in both graphs. I is in fact not tight in H1. There we use the fact that I is not tight in G. So therefore there we got a strict inequality. B of H1 is strictly less than B of H11 plus H12, and here we got a less than equal to. It could be tight, it may not be tight, we don't know. So that's what we have. Right, and if you put all of this together, we get this. But of course this is not written in the right order. If you want to be in the right order, at least the picture suggests that you should somehow combine these two to go here and these two to go here. Of course that is what the picture suggests, but you need to check that you are not being fooled by the picture. So let's do that. Let's think about these 2 graphs with respect to this graph. And this is where the interesting part comes. Observe that these 2 graphs are basically, we got to these 2 graphs from H1 and H2. But they are basically the I contractions of G1 up to multiplicities of edges. One of them is actually okay. One of them is straightforward. The other one is interesting. That is where we are using the lemma from the earlier lectures. You keep an even quadrant. Either you shrink the bottom, the odd part, into single vertex, and then you shrink this odd part into single vertex, or you first shrink the left side into single vertex and then the bottom part. These two graphs are actually the same. And there we are crucially using the fact that there are no edges between the two even quadrants. If there are edges between the even quadrants, then you can check that the graphs need not be isomorphic. Even the underlying simple graphs need not be isomorphic. Right? We have actually seen examples of this in an earlier lecture. Right? So that is where we are using a crucial point, that although this graph H21 is not the same as G12, it is the same up to multiplicities of edges. The B does not depend upon multiple edges. Right? The tight cuts of a graph are exactly the same as the tight cuts of the underlying simple graph. So B does not depend on multiple edges. So they are the same up to multiple edges. And therefore the B of G12 is equal to B of H21. I did not really write down, I did not draw G11, G21 and all these graphs. But they are the same as these up to multiplicities of edges. Therefore I can group these together. And we also observe that I and U are in fact tight cuts in G1 and G2. This is very crucial. Because they are tight cuts, this is exactly equal to B of G1 and this is exactly equal to B of G2. And we are done. Proof is finished. Questions, concerns?
I have one question.
Yes.
That when we are proving that in G1 that I is tight, so we are assuming that I is not tight, and so we assume that there are cut and there are perfect matching which intersect I 3 or more edges.
Right.
So there are only one edge which can go to X bar.
Right.
So at least 2 edges are going to go there.
Right.
X intersection Y bar.
Right.
And now we are extending that perfect matching to our original graph.
Right.
So how can we extend the perfect matching? Because C is a separating cut. If
Right.
it is tight cut, then it's.
So one way to extend, it's a perfect matching here, right? So it will contain one edge incident at X bar. Take the same edge incident at X in this graph and take a perfect matching containing that edge in this graph. Observe that the union is a perfect matching here. So whenever you have a cut contraction with respect to a separating cut, you can always take the other cut contraction and take a perfect matching there and here containing the same edge in the cut. Union is a perfect matching in the original graph. Yeah? Yeah. So yeah, for every separating cut also you can make the same statement. Every perfect matching of a contraction can be extended to a perfect matching of the original graph. It goes through for separating cuts also. Yeah? Good. Any other questions, concerns? Is everybody convinced about the subadditivity of B? Right? Okay, so that actually basically finishes chapter 4. The only thing I have not done is I have not listed down a bunch of corollaries. So you can go through them, or I may also just list them down in the next lecture, the ones that I find interesting. But yeah, I would suggest just go through the corollaries and try to observe all of them on your own using the results you've already proved, right? Some of them might be exercises on future assignments because that's how, in Lucas-Murthy, some of the exercises are just like prove that corollary, prove that proposition. So those might happen. But in general, since you have completed the entire chapter, I would suggest going through all the corollaries and making sure that you believe them. And if you don't, then let me know, then we can talk to the authors. But hopefully there are not many major typos, so it should be fine. Yeah. Okay. Any questions, concerns? No? Alright, so that's all for today and for the week. And we continue next week. We start chapter 5, characterizations of bricks and braces. Braces is easy because it's bipartite. Bricks is the one that is non-trivial. We will be proving in particular, the main goal of the next chapter is to prove the ELP theorem, the Edmonds-Lewis-Poly-Blank theorem, which says that whenever there is a non-trivial tight cut, there is one that is either a barrier cut or a two-suppression cut. And this gives an equivalent characterization or definition of bricks. They are precisely the three connected bicritical graphs. In fact, in the literature, if you look at 1980s and 70s, bricks are generally defined as three connected bicritical graphs. It is only later, in 1982, that people realize, oh, they are exactly the non-bipartite matching code graphs that do not have any non-trivial tight cuts, which is today the standard definition. But back then, that was not the standard definition. Yeah. Okay, thank you. You must stop recording. Thank you.